In this lesson, we're going to be talking about stationary points. Now, to begin with, I should make it clear what a stationary point is. A stationary point is basically a maximum or a minimum on any graph. So just to be clear, I'm going to go ahead and draw on what a maximum and a minimum might actually look like. If you're looking at the graph of a function, this would be a maximum because this point over here is the highest point on the graph in the local vicinity. And then similarly, we could say that this point over here is a minimum because this point over here is the lowest point in the local vicinity as well. Now, on the actual graph of a function, there are actually going to be lots and lots of places where you find maximums and minimums. So let me go ahead and actually draw a graph for you right now. Now, as you can see, on the graph that I've just drawn over here, there are actually a few points where you hit a maximum and a minimum. Just looking at this shape, it looks like we have a maximum over here, but half of it's missing, and we also have one over here. And now if we look at this shape over here, it looks like we have a minimum over here and another one over here. Okay, so in this lesson, we'd like to find some kind of general method that we can use to actually identify where a maximum and a minimum will occur. Or to be more clear, we actually want to find a way that helps us identify the x values where these maximums and minimums actually occur. Now, in a sense, I like to think of maximums almost like they're the tops of hills. I mean, you could see this almost like you're walking up a hill to get to the top. And in a similar way, I like to think of minimums almost like they're the bottoms of valleys. Now again, if we actually want to identify the maximums and minimums on a graph like this, it's going to be very beneficial to actually look at the slopes as we move across the graph. So let's turn our attention to this maximum over here. And let's imagine somebody actually walking along this maximum to get to the top. Okay, so let's actually observe the slope of this person as they walk up and down the hill. On the way up, I want you to notice that the slope is actually positive. And when the person makes it over the hill, their slope actually turns to become negative. Now, if on the way up the slope was positive, and on the way down the slope is negative, then at the top of the hill, the slope was exactly 0. This makes sense because you can't go from a positive number to a negative number without crossing 0 at some point. So therefore, we can see that when the slope is exactly 0, we must be at the top of a hill. And now we can apply similar reasoning to a valley. What actually happens on a valley? Well, as you can see, if a person started walking down the hill, you'd notice that their slope was negative the entire time. Once they pass this bottom point, then their slope becomes positive. And now we can actually make the exact same argument we made for the hill. If the slope over here is negative, and the slope over here is positive, then at the bottom of the hill, the slope must have also been 0. Again, this is because if you transition from a negative number to a positive number, you have to go through 0 somewhere. Now, from this it seems like, anytime you're at a maximum or a minimum, the slope of your curve is exactly equal to 0 in both cases. However, keep in mind, since it's positive here and negative here, it's only going to be 0 for a really tiny sliver of time. Okay, so if we know that the slope of the function should be equal to 0, didn't we say that the derivative actually finds the slope of the function? So, because the derivative is the same thing as the slope, if we want the slope to be 0, then the derivative also has to equal 0. So to be clear, this condition is always going to be true anytime you have a maximum or a minimum on your graph. And now, because this condition has to be true, we can actually use it to solve for maximums and minimums on our graph. Now, to actually show you how we'd use this, let me give you an example that we can work through together. Okay, so I want you to imagine that we had a metal beam supported on one side of a wall. Now I want you to imagine that I've supported it at some particular place. Now, I want you to imagine that we actually put a weight right at the end of this beam, and then you'll actually see it deform in some predictable way. Okay, so as you can see, the beam is actually bent into this new shape over here. Now, suppose we wanted to actually find out how far away this point was from the wall where the bending occurred. Well, the first thing we're going to need is we're going to need some kind of reference line. So let me go ahead and draw that in. Okay, so now that we've done this, we can go ahead and measure how far different parts of the beam are from this reference line. Now, in this picture, I've really exaggerated the amount of bending that's occurred. This is something that an engineer will do really frequently to help them find the areas where there's a lot of bending. Okay, so to make really accurate measurements, we use a tool called a caliper. And after we do this, we get these following points. So, we used a caliper to actually make these measurements over here. And a caliper is incredibly accurate, so we measure the amount of bending in this unit known as a micrometer. A micrometer is actually just 1/1,000,000th of a meter. Now, we decided to actually make these measurements at equally spaced intervals of 2 centimeters. Now, as we said, we wanted to find this position over here where the bending is at a maximum. To do this, we're going to need to find the derivative of these measurements somehow. Now, this is a problem because these measurements are just individual points. We don't know what the value will be right here. However, if we look at the shape that these points seem to make, they look a little bit like a cubic. If we use the line of best fit feature on some graphing software, or even on a spreadsheet, we end up with the following equation. So our graphing software tells us that 1.4x cubed minus 46x squared plus 350x plus 6 is the best graph that fits the data that we gathered. Now, in its own right, this function is actually pretty useful. We can go ahead and put in a distance from the wall, and it will tell us how much bending we have based on the data we gathered. So, for example, say we wanted the bending 10 centimeters away from the left wall. We could find this by just subbing in 10 for x into this equation. And then we could just use our calculator to figure out exactly how much bending this gives us. So, as we can see, when we're 10 centimeters away from the left wall, then the beam is actually bent up by 306 micrometers. Okay, so now that you understand what the function is telling us, we're after these 2 points over here, where there's the maximum bending in either direction. As we said, at these 2 points, the slopes have to be 0, and therefore we want f-x to be 0. Now, in order to make f-x equal 0, of course we need to find f-x, which we can do by differentiating this function over here. Okay, so in order to differentiate f of x, the first thing we're going to do is we're going to bring the power down over here, so that we're going to get 1.4 times 3, which is just the same thing as 4.2. Also, don't forget to subtract 1 from the power, so you go from cubed to squared. Okay, now after this we're going to go ahead and bring the 2 down and multiply it by the 46. 2 times 46 is 92. So now, of course, the derivative of 350x is just 350, and constants just disappear when we differentiate them. Okay, so as we can see, the derivative of this function over here is equal to this function right here. And now the next thing we'd like to do is to actually solve this function and set it equal to 0. We said that f-x should be the same thing as 0, so let's do that on the next line. Okay, now that I've actually switched the 2 sides, I hope you notice that we just have a normal quadratic to solve. And of course, we can always solve quadratics using the quadratic formula. So let me go ahead and put that on the page as well. Okay, so for starters, let's go ahead and substitute a. A is just 4.2, so let's replace it here and here. And now b is minus 92, so this minus b just becomes 92, and b squared is just 92 squared. Keep in mind that it's 92 squared because minus 92 times minus 92 is just the same thing as 92 squared. And now the final value we have to look at is this 350, which is the same thing as c, so let's replace that as well. Okay, so now we can just substitute this into our calculator to find the 2 x values where we get the maximum and the minimum. Let me go ahead and do the positive value first. Okay, so this is actually really cool. We can see that the positive value over here corresponds to this minimum right here, at x equals 17 centimeters from the left wall. Now we can just go ahead and swap this plus for a minus to get the negative value as well. So as we can easily see, the negative value over here corresponds to the x value of 4.9. Let's go ahead and actually mark both of these points directly on this bending graph. Now, just like we did for this random point over here, we can also substitute these points into our function to figure out what their y values are as well. Okay, so to find the y value, or the deflection at 17, we replace all the x's for 17s in the original function. Plugging this into our calculator will actually give us the value we need. And as we can see, this gives us a maximum deflection of minus 459.8 at x equals 17, which looks about right. And now we can do the exact same thing for the value at 4.9. Let's just sub that into our calculator as well. So therefore, as we can see, at the maximum deflection where x equals 4.9 centimeters, we get a deflection of 781 micrometers, which again looks about right. So now we've actually completed our example here. As long as we have the function, by setting it equal to 0, we can go ahead and use that information to actually solve for the exact x values where the maximum and minimum occur. So as you can see, we can solve for maximums and minimums by using the condition that the derivative must be equal to 0. Now remember, f-x equals 0 whenever the slope is equal to 0, and that's always going to happen at any maximum or minimum, as you can see on this graph over here. Now this actually does work pretty well, but I do actually have a bit of a confession to make. However, this lesson's getting a little bit long, so I think I'm going to save my confession to the next lesson, so tune in to find out when this can go wrong.